All right, so this is the divergence theorem. Again, a good amount of it is notes, the kind that you will have to read on your own on the PDF, unfortunately. But hey, that is good for us. The proof for this theorem is in your textbook. I did not pull it over. All right, look at our first example. Verifying the divergence theorem for the vector field F and the surface S that contains the cone and the circular top of the cone. See the following figure. Assume that the surface is positively orientated. So let E be the solid cone enclosed by S to verify the theorem for this example. What we have to show is excuse me. All right, by calculating each integral separately. So to compute the triple integral, note that PIVF is equal to Px sub x plus Q sub y plus R sub z, which is 2. So therefore, the triple integral would look like okay, so the volume of the right circular cone is given by volume of right circular cone pi r squared h over 3, where h equals r equals 1. So what this little piece tells us is so 2 times the volume would just equal 2 pi over 3. To compute the flux integral, first note that S is a piecewise smooth. S can be written as a union of the smooth surfaces. Therefore, we break the flux into 2 pieces, one flux integral across the circular top of the cone, and one flux integral across the remaining portion of the cone. Call the circular top S1 and the under portion S2. So we start by calculating the flux across the circular top of the cone. Notice that S1 would have the following whatever thing. I'll try to squeeze it in here, but we're probably gonna have to go on the side. So we would have RUV U. And it's going to be from 0 to U, and then to 1, and then 0 to V to 2 pi. And then we have to then we have our tangents. Okay, so then I have to add another slide for us, probably maybe 2. So then the flux across S1 is going to be that's a V on next. All right, and then it's going to be from 0 to 1, 0 to 2 pi, U minus U squared, sine V, dV, du. So the answer would be pi for that piece. Okay, so now we need to calculate the flux over S sub 2. So we have enough room on the next slide. I'm going to start it here and then we'll move over to the next slide. So the parameterization of S2 would be R U V U cosine V U sine V U. And then 0 to 1, and then 0 to pi. And I'll do the tangents on the next line. So we're going to have TU is going to be cosine V sine V1. Then we have TV which is negative u sine v u cosine v 1. Nope, 0, sorry. So then if we do tu cross tv, we get negative u cosine v I think I need to move that to a different line. Going to be negative u cosine v negative u sine v u. Notice that the negative signs on the x and y components induce the negative or inward orientation of the cone. Since the surface is positively orientated, we use vector. So we're going to change the signs. Positively orientated. So because of that, we're going to make it u cosine v, u sine v, negative u. All right, so then we have the flux across S2 as 0 to 1, 0 to 2 pi, u cosine v minus u sine v, u cosine v plus u minus sine v dot. I'll squeeze this other piece in. Actually, it's just this piece. dv du. Okay, so then it's 0 to 1, 0 to 2 pi. U squared cosine squared v plus 2u squared sine v minus u squared dv du gives us negative pi over 3 for that piece. So then the total flux across the whole of S would be pi minus pi over 3, which would be 2 pi over 3, which is equal to that triple integral. So then we have verified the divergence theorem because of that. All right. Okay. Calculate the surface integral where S is the cylinder, including the circular top. All right. We would calculate the integral without the divergence theorem, but the calculation not straightforward. So by contrast, we're going to use this one. Okay. So you may obviously have some fun if you would like and drive yourself a little crazy and try to figure this out the harder way. Excuse me. I would not recommend it. Guess if anyone's planning on going to like graduate school, be something you can dive into. 0 to 2 pi, 0, 1, 0 to 2, r squared plus 1, r dz, dr, d theta. So then that just becomes 3 halves on the outside, 0 to 2 pi, d theta, which is just 3 pi. Right? Sorry, we are moving a little bit quicker. We don't have that much time left and not a lot of problems, thankfully. All right, so here's your problem. You can read it later. So the solution, the rate of fluid across the S, you want to think about so by calculating the flux integral, let's discuss the value the integral should be. So based on the figure, we see that we place this cube in the fluid as long as the cube doesn't encompass the origin. Then the rate of the fluid entering the cube is the same as the rate of the fluid exiting the cube. The field is rotational in nature, and for a given circle parallel to the xy plane that has a center on the z-axis, sorry. The vectors along the circle are all the same magnitude. That is how we can see the flow rate is the same entering and exiting the cube. The flow into the cube cancels the flow out of the cube, and therefore the flow rate of the fluid across the cube should be 0. To verify this intuition, we need to calculate the flux integral. Calculating the flux integral directly requires breaking the flux into 6 separate flux integrals, one of each of the faces of the cube. We also need to find tangent vectors, compute the cross product, and use equation 619. However, using the divergence theorem makes this calculation go much more quickly. So we have what we just wrote down. That becomes a triple there you go. So therefore, the flux is 0 as expected. Okay. All right. Verify that the divergence of FR is 0, where FR is defined away from the origin. So R is going to be x squared plus y squared plus z squared. So the quotient rule gives all right. I guess they're just using an example in order to all right, we'll rock with it. So the quotient rule would give us Might have to get an extra slide just because I'm getting tired, so I'm writing much bigger. So then we have r cubed minus 3x squared r over r to the 6, r squared minus 3x squared over r to the 5th. All right, so similarly, we would do the same thing for y, but and z, so they don't show all the pieces because it's very similar. Okay, so then we would just do the DIVFR. So that's going to be, oops, we'll get a new slide in there. So DIVFR, r squared minus 3x squared over r to the 5th plus r squared minus 3y squared over r to the 5th plus r squared minus 3. Oh, those are, wait, yeah, I was right. I just need a z here. Did I put the right variables in last time? Sure didn't. Okay. All right, now we have that step. Then we would do 3 r squared minus 3 x squared plus y squared plus z squared all over r to the 5th, which is 3r squared minus 3r squared over r to the 5th, so that is 0. And that is what they wanted. Okay. Really quickly, we'll just do the last one. Here's the theorem for you. Has the proof, further information for you. All right, so last example. Sorry, we're going a few minutes over, but we'll be able to have 2 days of review, which you guys will all like. All right, so it says using Gauss's law, suppose that we have 4 stationary point changes in space with all of the charge of 0.002 coulombs. The charges are located at the following. Let E denote the electrostatic field generated by these points. I'm just gonna help us go super quick and put the solution on the slide. Just give me 1 second to get it in here. And then we will be good to go. Alrighty. Okay.